Okay, we are discussing the stability, right? That is given a bounded input where mod of xn is less than equal to capital M less than infinity. That is, however large this capital M be, the samples are restricted within a range. Okay, then my output for any n should not shoot up to infinity, it should be finite. If it is so, then we call it stable system. Stable in the BIBO sense, bounded input, bounded output sense. Now what is yn? I have to work out the convolution sum, right? H of r x n minus r, right? R from minus infinity to infinity. Many times I may not write the limits of r, but it's understood. Okay. So what is mod of yn? I want magnitude of yn not to shoot up to infinity. So what is mod of yn? That is mod of this. Mod of a summation is less than equal to sum of the mods. That is a triangle inequality. So it means this is and mod of a product is product of the mods. You know, mod of Z1, Z2 is same as mod Z1 into mod Z2. Z1 and Z2 being two complex numbers. If you are in doubt, put Z1 as R1 into the power J theta 1 and Z2 as R2 into the power J theta 2. That is in the polar form. Immediately the result follows. Product is R1 into R2. R1 into R2, right? And then, right? Now, x n minus r mod, that is just a mod value of input sample, and each input sample is limited to plus capital M or minus capital M. That is, mod value is less than equal to capital M. So this whole summation, if I now take all these samples and equate them to M, then again it is less than equal to, and M goes outside. Okay. Now, if this quantity summation mod h of r minus infinity to infinity, if this is finite, then certainly right hand side is finite because capital M is finite, which means mod yn is finite. So this is a sufficient condition that for stability this is the sufficient condition. Sufficient condition means if this is true, I will always have stable system. But I am not saying that if this is not true, I will never have stable system. So far I have not said this. I will explain this point. If it is less than infinity, and this is called absolute summability. Absolute means mod value. You take the absolute value or mod value of HR, then sum. If this is summable, that is if it is finite, if it is not infinity, if it is finite, then certainly mod yn is finite, because finite number into finite number is a finite number. That is, this is guaranteed. But is it a necessary condition? That is not satisfied. That is, suppose this is not less than infinity, but this is indeed equal to infinity. Does it mean that mod yn will indeed shoot up to infinity? From here I cannot say anything. That is, if I put infinity here, m into infinity is infinity, which means mod of yn is less than equal to infinity. So that means it could either be finite, because it is less than equal to infinity, or it could be equal to infinity. Both are possible, isn't it? If you just look at this expression, both are possible. So it may appear to us that if this is not satisfied, okay, system still may be stable, may not be stable. But now I say that no, this is also a necessary condition, because if this is not satisfied, system won't be stable. In what sense? In this sense, that if you give me this thing, that is, this is not absolutely summable, this is equal to infinity. Okay, I agree here that mod of yn may be less than infinity or may be equal to infinity, but at least it could sometimes become equal to infinity. Even those cases have to be discarded, should not be, even those cases are not acceptable, isn't it? If my system is stable, its output for any bounded input, output should always be finite. I should not leave any possibility of my output, at least for certain n, if not for all n, shooting up to infinity. Okay. Here, both the options are open. Mod yn could be less than infinity, in which case fine, or it could be equal to infinity. I'll show that if you give me this, I can construct one input in a very special way, so that for that input, and the input will be bounded. For that bounded input, under this condition, I'll show that mod yn indeed shoots up to infinity. So if this is satisfied, if this is not satisfied, at least there is one input sequence for which output shoots up to infinity. So at least for that input sequence, system is not stable. That means system is not stable. If it is to be stable, it has to be stable independent of the input given. I can construct a special input in a clever way. Suppose I construct an input like this, where x of n I take like this, h of minus n conjugate in case they are complex numbers, divided by h of minus n, if this is not 0 certainly. If it is 0, then I cannot do a division by 0, if this is not equal to 0, and 0 if h minus n equal to 0. What does it mean? What is x of 1? X of 1 is h star minus 1 by h minus 1. What is x minus 1? H star plus 1 by h plus 1. Likewise, if any of the h values is 0, then I don't do this division by 0, I take 0 value for xn. This way I can construct an input. Given impulse response sequence hn, which is not absolutely summable, I can create another sequence xn like this. It's in my hand. I create a sequence like this. Is it a bounded sequence? Answer is yes. Mod of xn is what? If xn is 0, then mod of xn is 0. Otherwise, here for this expression, what is mod of xn? 1. Apply mod. Okay, let me do one thing. Let me modify the definition. Let me put mod here already. Oh. Though it may not be required, but still, let me put mod already. Mod of h minus n. So if I take mod of xn, mod is already present here, so you have to apply simply mod here. And mod of a conjugate number, say mod of z star is same as mod z. Z is r into to the power j theta, z star means r into to the power minus j theta. Mod z is equal to r in either case. So mod of h star minus n is same as mod of h minus n. And mod of h minus n by mod of h minus n, that is equal to 1. So mod of xn is either 1 or 0. It's bounded. Okay, but how about y0? Yn I can find out. I'm taking a specific case, y0. So work out the convolution. H of r, x, n minus r, n is 0. So x minus r. Okay, I have given a bounded input. I'm finding out output say at n equal to 0. I can find out by working out the convolution sum for n equal to 0. So I have put n equal to 0, 0 minus r means minus r. Now as r moves from minus infinity to infinity, I get various values of hr. Whenever hr is 0, that doesn't contribute anything in the summation, because whenever hr is 0, corresponding x will be 0, because what is x minus r? I have defined xr. What is x minus r? X minus r by my definition is h star r by mod hr, if this is not 0, otherwise 0, if hr is 0, right? So in this summation, consider only those cases where hr is non-zero, because if hr is 0, this value is 0, and x minus r will be 0 if hr is 0 by definition. So only concentrate on those cases in this summation. And there what is happening? hr as it is, replace this x minus r by this expression, h star r by mod hr. What is in the numerator? H into H star means mod H square divided by mod H. So what you are getting? Not HR, mod H square divided by mod H. Mod H of R. But you have given me an unstable system. You have given me this fact that mod of HR is infinity. When summed, sum of mod HR is infinity. That was given. So this is equal to infinity. So at least at n equal to 0, this value should sub to infinity, even though I gave a bounded input. So at least for this input, I have shown that even though input is bounded, when the absolute summability condition was not satisfied, I can get one unbounded sequence like this, which should sub to infinity at least at n equal to 0. I presume that one can cleverly construct many such sequences which are bounded, but under the absolute summability not satisfied condition, you can again construct such examples where output should sub to infinity at some point or at many points. Okay, so at least for those inputs, the system works in an unstable manner. So if the system works in an unstable manner, even for one input, I will consider the system to be unstable. So this condition is both necessary and sufficient. Okay, just quickly take one example of how to carry out convolution. Suppose xn is a to the power n un, and there is xn is like this. X of, instead of n, I plot it like x of r, a to the power n. This is 1, then a square, a cube, like this. Okay, another sequence is say hn, which is equal to 1 for n equal to 0, 1 up to some capital N minus 1, 0 elsewhere. That is, h of n is nothing but u of n minus u of n minus capital N using unit step functions. Okay, you have to convolve the two. What is convolution? Y of n, you can write it either x convolved with h or h convolved with x. Suppose you write like this, x of r into h n minus r, r from minus infinity to infinity. If you do this, how do I go about it? Okay, suppose I want to find out, let me plot this h of r also. Zero, 0, 0. Suppose I want to find out y of 0 first. Then I will find out y1, y minus 1, y2, y minus 1, like that. How to find out y of 0? Simply xr into h minus r. Term by term product. For r equal to 0, multiply the 2. For r equal to 1, multiply the 2, and like that, and then add. And that will give you y0. But here I am getting h minus r. H minus r, giving h of r like this. What is h of minus r? Reverse it. Okay, whatever is occurring at r equal to 1, h of 1, that will occur at minus 1, because minus of minus 1 is plus 1. So h minus r right, and now you take this sequence and this sequence, do a term by term product, sample by sample, and add. These two sequences overlap only at this point, this sample and this sample, right? So what is that value? That value is 1 into 1. A to the power 0 is 1, so 1 into 1, 1. This is equal to 1, right? How about y minus 1? Y minus 1 means you have to put h minus 1 minus r. Or in general, how how to go about for yn? We have plotted h minus r. But here I want h n minus r. H n minus r is nothing but H, see, I redraw the sequences again. H minus R I am plotting directly. Okay. How about H n minus R? H n minus R is what? H of minus R minus n. If H of minus R, you call, to avoid confusion, you give a name G of R. G of R is suppose equal to H minus R. Then how about H of minus within bracket R minus n? That will be G of R minus n. So I am interested in, if I call H minus R as G of R, then I am interested in finding out what is G of R minus n. That will give me H n minus R. If it is G of R, then G of R minus n will be what? N is by your choice. N was fixed from outside the convolution sum. So n is a constant. All these x's are in terms of R. So this is GR. What is GR minus n? Shifted right or left depending on the sign of n, but shifted by n bits. If n is negative, there will be advanced. So this thing will be shifted further to the left and there will be no overlap. So you'll get 0. So yn clearly is 0 whenever this n is less than 0. If n is negative, this whole chunk will be shifted further to the left and these two will not overlap. So your output will be 0. So yn is 0 for all n less than 0. On the other hand, if n is positive, then what will happen? If n is 1 for that matter, this will be shifted to the right by 1. If n is 2, this will be shifted to the right by 2. So during this time, some of the tail will be on this side which will not overlap, and some part of this sequence will overlap with this fellow. Now if you carry out the term by term product and sum, you have to take on only this part. Okay. Till what point of time, till what index point, I will have this situation where there will be some tail. Yeah, I can go up to small n equal to capital N minus 1. When small n equal to capital N minus 1, this whole chunk will come below it. Okay, so for till that time, there is for n greater than equal to 0, less than equal to capital N minus 1, what will be the convolution? If suppose my n is somewhere here, then I will have some ones, 1 here, 1 here, 1 here up to this. Only these ones will be multiplied by the respective samples here and added. So what will that be? A to the power 0 into 1 plus a to the power 1 into 1 plus a to the power 2 into 1 and like that up to a to the power n into 1 again. So here yn will be a to the power 0 plus a to the power 1 plus dot 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 plus a to the power n. This is 1 minus dp series. After this, for all n greater than equal to capital N, what will happen? This chunk will now move here, isn't it? No such tail here, total overlap. Heading point will be the nth point. So what will be the summation? A to the power n from here into 1 plus a to the power n minus 1 at n minus 1th point into again 1, and likewise total n such points. So here yn will be a to the power n, that is the heading point, header point, front point into 1. Then the one previous to that is a to the power n minus 1, again 1 from here, and likewise up to a to the power n minus take this as common, then what will happen? From here within bracket, say 1 plus a plus a square plus dot dot plus a to the power n minus 1, which makes it what? Into 1 minus a to the power n divided by 1 minus a. That is how we carry out convolution graphically. Okay. Next comes the idea of eigensequence of a linear time invariant system. What is meant by eigensequence? You have studied eigenvector, eigenvalue probability in matrix. Suppose I give you a n by n matrix. It is also a system. System is the matrix. Its input is one vector. Output is computed by taking the matrix vector product, even another vector. This is also a system. One input, one output. So any input will give rise to some output vector, I agree. Input is x, matrix is A, capital A. So capital A times x is your output vector y. Right? So this is the general situation. It's not necessary that output y will be similar to x always. But sometimes it so happens that the output y, that is equal to a into x, is nothing but x itself, just multiplied by some constant lambda. That lambda multiplies each component in the vector x. Lambda could be a gain factor or attenuating factor, whichever way. Okay. Then I call that particular x to be an eigenvector of matrix A. Similarly, for such LTI system, okay, I know that given any input xn, I get a general output yn as xn convolved with hn, and that output may not be similar in appearance to xn. It's a general output. In arbitrary input xn, arbitrary output yn. Right? But sometimes it may so happen that output that you get for a particular choice of your input is such that output will be nothing but the input itself, just all the samples multiplied by some constant number. If that happens, then that input sequence will be called an eigensequence for LTI system. Suppose I consider xn like some constant a times n. Then what is yn? X n minus r hr. And what is x n minus r? A to the power hr. You see, both n and r, they are occurring in the power, and therefore they are separable. That is the key. A to the power n minus r is nothing but a to the power n into a to the power minus r. So they are separable, and a to the power n can be brought outside the summation because it does not depend on r. So you will get a to the power n back, a to the power n here, again a to the power n into a quantity Now this quantity does not depend on n. It's a constant. It only depends on your choice of A. Sequence is this. So it is like some eigenvalue lambda which depends on A. For your choice of A, compute this once for all. So output is nothing but a to the power n multiplied by lambda A. So a to the power n is a sequence. This form is a sequence which is typically an eigensequence of a LTI system. You can give any value of A. Now, of all values, there is a particular value, but we choose for A, and regions will be obvious. We take A to be e to the power j omega. Omega is radian. It's a digital frequency, it's called radian. Its unit is radian. E to the power j omega. That is, A is a complex number of magnitude 1, phase j omega. Okay, if I take that, then I have e to the power j omega n. And what is my yn? Yn is, instead of using the lambda notation, I adopt this notation h e to the power j omega e to the power n. These and these are same. What is this h e to the power j omega? This is equivalent to your lambda a, but I am using a different notation here. Also, why this notation I will explain. But what is this in this case? It is nothing but the eigenvalue. I am writing using this notation. What is this? This summation h of r e to the power minus j omega r. Okay. So this depends on omega. So I could have written this simply a function of omega. But I always write it as a function of e to the power j omega, because in this summation e to the power j omega, which is occurring in the power. Suppose you work out this summation, it looks like suppose GP series. Suppose it so happens it is a GP series. You will get it not only as a function of j omega, but rather totally as a function of e to the power j omega. It is this e to the power j omega or its powers which will occur in that overall expression. But yes, if you want, you could still write it as a function of j omega. But it is a notation which is accepted universally. Okay. So your output yn is nothing but a to the power, this a to the power n should have been written as into e to the power j omega n. Okay. So output is this, where h e to the power j omega is this. Okay. Question is, why did I go for this e to the power j omega? Why? Firstly, though I computed this quantity for the specified h of n, which was the impulse response of a sequence, but now I can say that whether it is an impulse response or not, given any sequence, I can work out a sum like this on it. For instance, given xn, I can call capital X to the power j omega as summation xn e to the power minus j omega n, a similar sum. Okay, the question is why I was so interested in not retaining a but taking the specific form e to the power j omega n. There are two answers. One is, given xn or hn, I can run this summation and yes, I can get these functions. But given this, can I find out xn? Answer is yes, I can. If you take a to be e to the power j omega, but if you take a general a, then possibly you cannot. For a equal to e to the power j omega, how do you do that? What I do that, suppose you want to find out x of say m. Given this function as a function of omega, you want to find out x of m for any finite m, for any index m. How do I do that? I take an integral of left hand side, but before that I take this guy and suppose multiply this side by e to the power j omega m, and then integrate it. Integrate from what point to what point? From minus pi to pi. What happens to the right hand side? Right hand side also have to multiply the right hand side by e to the power j omega m, this quantity, and again integrate with respect to omega over the same range. Okay. Now the discrete sum and integral, they can be interchanged. So keep the, assuming that both the discrete sum and integral they exist, then only two summations can be interchanged. So suppose you take the summation outside, discrete sum outside, bring the integral inside, minus pi to pi, x of n can be kept here. So you simply have e to the power j omega m minus n d omega. Alright. Now m is your choice. You wanted to find out x of m at a particular m. That m is your choice. But n is the running index. Suppose n is not equal to m, then this is an integer. If you work out this integral, it will amount to 0. If this is an integer, non-zero integer. How? If you work out the integral, what will you get? Mathematically speaking, this factor will come in the denominator. Then e to the power j omega times the integer. You can call this integer to be k. So e to the power j omega k by k. By jk, rather j also will come. E to the power j omega k being integrated, so we will get e to the power j omega k divided by j into k. J into k is of no use to me. That e to the power j omega k, take k equal to pi, omega equal to pi, so e to the power j into k into pi minus e to the power minus j k pi. So it will be twice j sine k pi. And sine of any integral multiple of pi is 0. Sine pi is 0, sine 2 pi is 0, like that. So it is 0. Physically, it is like this, taking a sinusoid. See, if you plot this function as a function of omega, omega is continuous. Okay, this is some say k. So it will be j into k into omega. If you plot it, like you know how to plot it, it will be j into k into t. Instead of t as a continuous variable, I have omega as continuous variable. It will still have, it will be sinusoidal function. So if you take an sinusoidal function like this, integrate over one period, you will get 0, isn't it? Minus pi to pi is one period, or integral multiple of a period. If it is e to the power j omega into k, suppose it is e to the power j omega only. What is its period? If omega is replaced by omega plus 2 pi, you get back e to the power j omega, because e to the power j 2 pi is 1. Are you understanding what I am saying? Giving e to the power j omega, its periodicity is, what is its period? 2 pi. Because e to the power j within bracket omega plus 2 pi is equal to e to the power j omega. Because e to the power j 2 pi is 1. If it is e to the power j omega into k, then what is the period? 2 pi by k. Take e to the power j within bracket omega plus 2 pi by k. Then outside k, so that k will cancel, isn't it? Which means 2 pi will be k times the period. But if you take a sinusoidal function and take k cycles, integrate over it, you will still get 0. So that is what is happening. So whenever you have got a non-zero k here, this integral will be 0. Only when n is equal to m, then e to the power 0 is 1, and then 2 pi will come over, and outside n equal to m. So 2 pi into xm. So xm means this thing. If I take 1 by 2 pi here, 1 by 2 pi here, so this quantity will give you, this will give you x of m. Okay. I rewrite this again. That means x of n is, and this is called the inverse formula. Okay. This is one formula. The other formula was, that is giving this, how to find out xn. This is called the inverse discrete Fourier transform formula. Discrete time Fourier transform. And given xn, how to find out capital X e to the power j omega. That was the discrete summation. This is the DTFT, not DFT, DTFT, discrete time Fourier transform. This is a discrete time sequence, it's Fourier transform. It's a new definition. Okay. And this is what? The inverse of it, so I call it IDTFT. Inverse discrete time Fourier transform. So there is one reason why I opted for e to the power j omega as A. That is, one can be obtained from the other and vice versa. Secondly, there is another advantage. Suppose this xn is inputted to a LTI system. So my yn is what? Capital T operator working on xn. That is capital T working on this whole thing. This integral also is a summation, continuous summation over omega. Within this range, for each choice of omega, you have got some value here multiplied by a function e to the power j omega n, which is a sequence. Take another omega within this range, you get another value here. Then for that omega again another sequence. And all are summed. Only thing, it is not a discrete sum, it is a continuous summation, that is why it is a definite integral. But using linearity, I know capital T then can be brought within this summation, and capital T working on this total, this product is nothing but this times capital T working on this itself, and capital T working on this means what? This is an eigen sequence. So the sequence itself multiplied by what? Capital T working on this. That will give back sequence itself into h e to the power j omega. Isn't it? This was equivalent to the eigenvalue into d omega. That is, within this summation I have got so many harmonics. You see, within this summation xn I have got so many harmonics from minus pi to pi. Omega is continuous. Each harmonic is represented by e to the power j omega in sequence, with a magnitude factor this, with an amplitude factor this, which is having both magnitude and phase. It's a complex number. Each of them, as they pass through the system, is multiplied by this function. So either magnitude wise the whole thing goes up or goes down, depending on whether at that frequency of gain or attenuation, there could be phase shift and all that. And then again, all these harmonics are superimposed by this continuous integral. This gives the idea of filtering. That for certain, you can design your system such that designing system means designing this factor. This comes from the impulse response of system, right? So you can design it such that at certain omega within this range, this could be having high magnitude, and certain other omega, it could be having low magnitude. So those harmonics, certain harmonics are passed, others are not passed. This gives rise to the idea of filtering. Another thing, if yn has got discrete time Fourier transform, capital Y e to the power j omega, then yn is again by the corresponding IDTFT formula for yn, I should have had right. So yn is this, again yn is this. So that means these two integrals are same, identical. Okay. So you can simply equate, take this part to be, you can identify this part to be equal to y to the power j omega. Which means DTFT of output sequence is the product of the two DTFTs. That is, in frequency domain, the two DTFTs get multiplied to give you the output DTFT. Okay. Now, some of the properties, x e to the power j omega, this is equal to, I know, xn e to the power minus j omega n, right? This function is a periodic function. This is periodic in omega. If you have x e to the power j omega plus 2 pi, suppose, what will you get? Instead of omega, if you put omega plus 2 pi, what will you get? E to the power minus j 2 pi into n, that is always 1. E to the power j 2 pi, e to the power minus j 2 pi, e to the power j 4 pi, e to the power minus j 4 pi, whatever it is, it's always 1. So you will get back this quantity only. If you take this omega, replace this omega by omega plus 2 pi in this summation. Okay, what will you get? E to the power minus j omega into n will remain as it is. Another factor will come, e to the power minus j 2 pi n, and that is always 1. Isn't it? So you get back this summation. So whether you put plus 2 pi here, minus 2 pi here, whatever. So this is equivalent to x e to the power j omega. So this quantity is periodic over a period 2 pi. So when I plot this, I will always take the period to be starting from minus pi to pi. You could take any point and go 2 pi to the right and 2 pi to the left, but my style is to take from minus pi to pi. If I have the entire information within that, I don't need the information to the right or to the left because it's periodic. Okay, there's one more thing you see. I using convolution sum and that little bit complicated algebra showed that two LTI systems can be interchanged. But then I had to really work out those discrete sums and all those things. But the whole thing can be represented, whole thing can be worked out in a much easier way in the DTFT domain. How? If you have xn h1n yn, and suppose I write like this. This is my notation. Whenever I write xn, this bidirectional arrow, capital X e to the power j omega, it means xn has a DTFT this, and this has an IDTFT this. So if xn has discrete time Fourier transform this, h1n has this, and yn has this, then what is y e to the power j omega here? h2 e to the power j omega into DTFT here, and DTFT here is h1 e to the power j omega into x e to the power j omega. That is h2 e to the power j omega into h1 e to the power j omega into x e to the power j omega. But the product, it is just a product which is always commutative. So you can have h1 first, then followed by h2. Okay, that is you can have h1 e to the power j omega followed by h2 e to the power j omega into x e to the power j omega. And what does it mean? First x is processed by h2, so that the output of that system has DTFT equal to the product of the two DTFTs. That processed by h1, so the final output DTFT is input DTFT into the corresponding system's impulse responses DTFT. Okay, so this DTFT of the impulse response of a sequence is called transfer function of a system, right? When will the DTFT exist? We have already worked out the formula of IDTFT and DTFT. We have proved that DTFT is a periodic function of period 2 pi. We have also proved that output DTFT of LTI system is nothing but product of two DTFTs, one of the input, one of the impulse response. Okay, all this we have proved. Now, DTFT consists of infinite summation, right? Infinite summation. What is DTFT? This is the DTFT. This infinite summation, where n starts from say minus infinity to infinity, for DTFT to exist, this must converge. That is mod of should exist. There is mod of this should exist, but mod of this is less than equal to mod of this, and mod of this is what? Just mod of xn, because mod of this quantity is 1. So if this is finite, this will exist. So there is a sufficient condition. So sufficient condition for DTFT to exist is that the sequence should be this n is from minus infinity here. This is the sufficient condition. Okay, so I stop here today. In the next class, we'll start from here. We'll get into some of the properties of DTFT and its relation to analog Fourier transform, and we'll also consider a particular class of system called rational systems. Okay, then from that we'll move into jet transform and we'll slowly develop the background that is required to get into multi-rate DSP and other related topics. Okay, Thank you very much.